Hello and welcome to Bedroom Physics. Today I'm going to be analyzing the speaker interference problem. Some of you may know Professor Simpson and I are in a competition to see who makes the better video, and so I thought before we start we could reflect on some words by Matthew McConaughey. I am a football fan, a sports fan, a fan of competition. In any case, let's get started. I think the best way to approach this problem is thinking of it in a more general sense than a specific case. If we look at the problem, the goal here is to find the difference between the length of this distance and the length of that distance. Now, if we break the distances down, you will see that this line has both an x and y component, and so the distance of the line will be the magnitude of the line. That is Pythagorean theorem, that is the square root of x squared plus y squared. And as we can see, the x component for this line, for the bottom line, will be just the change in x. And the y component for this line will be the change in y. The x component for the top line will be change in x, and the y component for the top line will be some constant y minus change in y. And so now we have two vectors. The top vector I'll name S2. And it's equal to change in x, comma, y, minus change in y. And it's minus change in y. It could be change in y minus y. Either one kind of works because we're squaring it, so the negative doesn't really matter. But as you can see, as y, or should I say, as change in y gets smaller, then our y component will become larger. And as our change in y gets larger, we will eventually reach 0, but then if we go into the negatives, it will get larger in the negatives, or technically it's getting really, really small. And of course, the bottom line is just following the changes that we're making. So S1, this is S2, S1 is equal to change in x and change in y. And what we're looking for is the difference between them. However, these lines are represented by the magnitudes, not as the components. And so we're going to have the magnitude of S2 minus the magnitude of S1 is equal to the change in x. And of course, we'll substitute for that later on when I do the actual problem. But let's actually write it out as the complete formula. Okay, so now we have the complete formula. Let's say that we want to find when the change in x is its maximum, and also when the change in distance is at a minimum. In order to do this, we will find the derivative of this formula and set it equal to 0, and we should get a few values. This one specifically will have a couple values, or in other words, we'll have two values. So if we take the derivative, and of course the derivative will be in terms of x, there could be different things that we could be changing. Of course, this formula would look a lot bigger. I'm kind of doing a general case, but it's still a little bit specific. A more general case would really just be more complicated, and it wouldn't really help this specific problem but it kind of works the same way. It would be hard to show that it works the same way. So I think this is a really good example. Okay, so taking the derivative in terms of change in x. Okay, so I've taken the derivative and I've set it equal to 0. And as we can see in this equality, the equality will be true when the change in x is 0 or infinity. So our two critical points will be 0 and infinity. And when we plug in 0 and infinity to these equations, we will see that if we plug in infinity, we get infinity here, which dwarfs the change in y's, and infinity here. These will be the same sizes of infinity, so they will cancel out to 0. And if we plug in for 0, then we will only get the y's, which is greater than 0, and so that will be our maximum. Okay, so now we're just about ready to do the actual problem that was on the test and also on the homework. So in this case, we have d, which is the y distance, which was 4, and this 4 will be our constant y, and our L, which is changing, is greater than or equal to 5. In other words, this point is at 5 and we're going farther out. And so let's start plugging things in and setting things equal to each other. We're gonna have L squared plus 4, and of course our y here is not changing, there's only movement along the x-axis, so our change in y will just be 0 minus, and since our change in y is 0, then all we're left with is the change in x, or in this case just L, equals the change in s. However, in this problem we're looking for when the sound waves cancel each other out, and we know that that changing distance is equal to n, which is some positive integer, plus half times lambda. And so now we're going to set this change in distance equal to our interference formula, and we'll have L squared plus 4 squared minus L equals n plus 1/2 lambda. Now since we are moving away, we can go an infinite distance, and we know that at an infinite distance, n, or our change in s here, is going to get very small, or in other words, n is going to go to 0. Which means that in order to find the distances at which we have interference, we can actually start at 0 and keep going until our distance is past 5 going to the right, or in other words, when our distance ends up being less than 5, which we can't have. So ideally we want our final distance to be something a little bit past 5 when n is a positive integer. Okay, so let's do this first. Let's solve for L. Let's get L alone. And I've done this problem about 100 million times. So I'm just gonna see if I can remember it from memory. 16, which is 4 squared. And then I believe it's minus lambda squared n plus 1/2 squared over 2 lambda n plus half is equal to L, which is what we're looking for. If we plug in for 0, I believe that we're going to get 31.875. And of course this is all in meters. And if we plug in n equals 1, we'll have L equal to 10.3 meters. And of course when L equals 2, or I'm sorry, when n equals 2, L will be equal to 5.78 meters. And of course in this case our lambda is equal to 0.5, and again I'm just plugging in n equals 0, n equals 1, n equals 2, and this is because at n equals 0 we are a really far distance, and we can be at a really far distance because our change in L is getting larger. If we were moving closer, I would say the best approach would be to actually plug in for L when L is 0, and this will give you the starting point for n. And of course remember that n has to be a positive integer, and so if you get 7.5 for example, then you need to go a little bit farther or plug in for 7, and then you'll get your L. And then of course just keep going all the way down in n's until you reach a point where you're going past the point that you started, and if it is against the rules, then those n's of course do not count. In any case, this is my video, this is my analysis on the speaker interference problem. I hope this is of some help, and I'll see you guys in class and perhaps on the next concept video. Thank you.